Hello everyone. Today we will be discussing the topic flow through parallel pipes. So this is also coming under module 3. So in last section we have seen flow through series pipe, or it is also now called as compounding of pipes or flow through compound pipes, etc. Now in this session we will be looking into flow through parallel pipes and how it is different from that of the series connection or series pipes. So given is a figure that represents flow through parallel pipes. So here you can see that there is a main pipe which divides it into two branches as shown in figure, and again join together in the downstream to form a single pipe. So this is the main pipe, and here it is being divided into two pipes, and again at the downstream it is again being joined into a single pipe. So this arrangement is known as a parallel pipe arrangement. So the important thing to note in the case of parallel pipe is that discharge to the main pipe is increased. So wherever you want to increase the discharge, you should arrange the pipes in the parallel connection. So there are two important points to be noted in the case of parallel pipes. First one is the rate of flow, that is the discharge in the main pipe is equal to the sum of the rate of flow through the branch pipe, or we can write Q is equal to Q1 plus Q2. Recall that in series pipe we had same discharge in each pipe where Q1 was equal to Q2, whereas in the case of parallel pipes here the discharges will be added up, that is Q is equal to Q1 plus Q2. And the second important point is loss of head for each branch pipe is the same, that is loss of head for branch pipe 1 will be same as loss of head for branch pipe 2. Again recall that in the case of series pipes it was just the reverse, that is in series pipe the head loss due to friction was added up and the discharge was equal. It is just the reverse in the case of parallel pipes, wherein you have the discharge which is getting added up and the head loss due to friction in both the pipes will be equal. So as per Darcy's Weisbach equation we can write like this. And if we consider if F1 is equal to F2, where F1 and F2 are the, as you know, is the coefficient of friction, if both of these are given equal, then we can simplify this equation and the final equation will be L1 V1 square by 2G D1, which is equal to L2 V2 square by 2G D2. So this is the equation for parallel pipes. Now we will look at a problem to better understand the parallel pipe. So here is a problem. A main pipe divides into two parallel pipes which again forms one pipe as shown in figure. So this is the figure, the same figure that we just look into the last slide. The length and the diameter for the first parallel pipe are 200, 2000 meter and 1 meter respectively. The length of and the diameter of the second pipe are 2000 meter and 0.8 meter. Find the rate of flow in each of the parallel pipe if the total flow in the main pipe is 3 meter cube per second. The coefficient of friction for each parallel pipe is same and is equal to 0.005. So this is a question based upon parallel pipes. So here we have a single pipe which is getting divided into two parallel pipes, and you are given the diameter and length for both of these parallel pipe are given, and then the flow through the main pipe is also given. So now let us list these things. So let us list the given things, that is length of pipe 1, let it be L1 2000 meter, D1 diameter of pipe 1 meter, similarly for pipe 2 L2 and D2, and the total flow, that is flow through the main pipe, is 3 meter cube per second. That is also given in the problem, and the coefficient of friction is same, that is 0.005, and we are assuming let Q1 be the discharge in pipe 1 and Q2 be the discharge in pipe 2. So for parallel pipes, we know that the discharge will be the sum of the discharges in each pipe. So we can write Q is equal to Q1 plus Q2, which is given as 3 meter cube per second. Now, the equation for parallel pipe, we have already seen it. That is 4F1 L1 V1 square by 2 GD1, which is equal to 4F2 L2 V2 square by 2 GD2. Here again, F1 and F2 are same, so that will all be, that also will be simplified. Substituting those values, we do not know the value of V1 and we do not know the value of V2. So we substitute and substitute all other values, and finally what we get is V1 V1 square by 0.1 is equal to V2 square by 0.8, or we can write V1 is equal to V2 square, V1 is equal to V2 by root of 0.8 or V2 by 0.894. And we have to write Q1 and Q2. That is Q1, we already know that Q1 is equal to A1 V1. So substituting the value, A1 means it is a circular pipe, so cross section is circular, therefore the area is pi by 4 d1 square, and the value of d1 is 1 into v1. So v1, we have already got an expression for v1 in terms of v2, so we substitute it here and write it as q is equal to a1 v1, that is q1 is equal to pi by 4 1 square into, instead of v1 we substitute v2 by 0.894. And similarly q2 is a2 into v2, we substitute the value here, also we get the expression in terms of v2. So we ensure homogeneity, that is q1 and q2 is in the terms of v2. So once we have got the value of q1 and q2, we substitute in the first equation, that is total discharge q is equal to q1 plus q2. So substituting those values in this equation, we will get q1 in the place of q1 we have pi by 4 into v2 by 0.984, and q2 is pi by 4 into 0.64 into v2, which is equal to total q, which is 3. So on simplifying, we will get the answer of v as 2.17 meter per second. So we are asked to find out the discharge. So once we get v, or rather this is v2, okay, this is v2, and substituting the value of this v2 in our equation, v1 is equal to v2 by 0.984, we will get the value of v1 also. So from that we can find out discharge in each pipe. That is, discharge in the first pipe will be q1 is equal to a1 v1. Substituting the value, we will get the answer of q1 as 1.906 meter cube per second, and we can substitute q2 also in the similar manner, in this manner, or else we can substitute q2 is equal to total q minus q1. Both will be the same, so we get the value of q1 and q2. So let us look at another problem. This is slightly different problem. So a pipe of diameter 0.4 meter and length 2000 meter is connected to a reservoir at one end. The other end of the pipe is connected to a junction from its two pipes of length 1000 meter and diameter 300 mm run in parallel. These parallel pipes are connected to another reservoir which is having a level of water 10 meter below the water level of the above reservoir. Determine the total discharge if F is equal to 0.015. Neglect minor losses. So in this problem we have to draw a figure for better understanding of the problem. But before drawing that figure, let us list out the given things. So the diameter of the pipe, that is the main pipe, is given. This is 0.4 meter, and its length is also given. So L is equal to 2000 meter, and it is connected to another pipe, and the length of the parallel pipes. One is having a length of, both are having length of 1000 meter, and both are having diameter 300 mm. So the diameter and length of the parallel pipes, that is L1, which is equal to L2, which is equal to 1000 meter, and D1 is equal to D2 is equal to 0.3 meter. And both pipes are also having same coefficient of friction. So F is 0.015 for all the pipes. and the distance of water level in the two reservoirs is 10 meter. So we have to draw a figure here to solve the problem or to better understand the problem. So go ahead with this problem. We have to draw this figure. So in this figure there are two reservoirs. We are naming it as E and reservoir F, and water has to be supplied from E to F. E is at a higher height and F is at a lower height, and the height difference is 10 meters. So there is initially a pipeline AB which is having a length of 2000 meter and D is 0.4 meter, and the velocity we do not know, so we denote it by V. And there is a junction called B, and from this junction the pipe is divided into two parts, two parallel pipes. The specialty here is that two parallel pipes are having the same dimensions, that is length is same and the diameter is also same. So or in other words we can say that the velocity of flow in both of these parallel pipes will be the same, since we have the same diameter and length. So now we try to solve this problem. So first we apply Bernoulli's equation between the points E and F, that is between these two reservoirs, and we assume that first of all the flow is taking place through A, B and C. So applying Bernoulli's equation between E and F, we know that P by rho g, V square by 2g, etc. will be 0 because we have atmospheric pressures at both these reservoirs and also static conditions. So velocity also will be cancelled. Only thing remaining will be Ze minus Zf, which is equal to 10 meters. So we have LHS 10 meters, and that should be equal to the head loss due to friction. And this head loss due to friction we can split into two parts. That is, first one is head loss due to friction happening here, and then head loss due to friction happening here. So we denote it by 4FL V square by 2GD for the part AB, and 4F L1 V1 square by 2GD1 for the part BC. And substituting the values, we do not know the value of V and V1, so we'll get an expression 10 is equal to 15.29 V square plus 10.19 V1 square. Now, from continuity equation, we know that discharge through AB should be equal to the discharge through BC and discharge through BD. So that is the basic principle of parallel flow. That is, the discharges will be summed up or added up. So again, substituting those values, discharge through AB means pi by 4. This is AV, A into V. Pi by 4 d square into V should be equal to pi by 4 d1 square into V1, that is discharge through BC, and pi by 4 d1 square into V2, that is discharge through BD. So as I mentioned earlier, D1 and D2 are same, that is the length of the pipes BC and BD, that is those parallel pipes, are equal. So the discharge through BC should also be equal. So when the discharge is equal, it means that V1 should also be equal to V2. So we can simplify this equation. Pi by 4 d square, both replace this V2 by V1. So after simplification we will get the value like this, and finally we will get an expression V1 is equal to 0.888 V. Now we substitute this value of V1 in our earlier equation. So earlier we have got the equation 10 is equal to 15.29 V square into 10.19 V1 square. So in the place of V1 square we will substitute this value, and finally after simplification we will get the value of V as 0.654. So once the value of velocity is given, we can easily find out the discharge, that is Q is equal to AB. Finally we will get the answer 0.0822 meter cube per second. So hope you have understood the concept of flow through parallel pipes. We have discussed two problems. So you should keep in mind that the discharge in the case of parallel flow will be summed up or added up, that is Q is equal to Q1 plus Q2, and the head loss due to friction in the case of parallel pipes is the same, that is HF1 will be equal to HF2. These 2 points has to be kept in mind while solving the problems. Now we move to the next topic, that is flow through branched pipes. So what is branching of pipes or branched pipes? When three or more reservoirs are connected by means of pipes having one or more junctions, this system is known as a branching pipe system. So here we should keep in mind that here we have in earlier cases we had only two reservoirs, but in the case of branch pipe we have three or more reservoirs and they are connected by means of pipes having one or more junctions. Then we can say that it is a branch pipe case. So in branched pipe system, the length, diameters and coefficient of friction of each pipe will be given, and you will be asked to find out the discharge and the direction of the flow in each pipe. So three main equations are important here in the case of branch pipe. That is, first one is continuity equation, second one is Bernoulli's equation, and third one is Darcy's Weisbach equation. So it is also assumed that reservoirs are very large and the water surface levels in the reservoirs are constant, so that steady state condition exists in pipes. So another assumption in the case of branching of pipe is we are assuming the water surface level as steady conditions and minor losses are neglected that we have done throughout. The flow from reservoir A to from A takes place to junction D, and the flow from junction D is towards C. So you will understand what is written here better if you look at this figure. So this is an example of a branched pipe system wherein you have three different reservoirs A, B and C, and we have a junction here called D. Okay, so pipe initially flow takes place from A to D, and then from as the direction of flow indicates from D to B depending upon whether ZD or ZB is higher, and then from D to C. So we will look at look into detail. So the flow from A to D, we apply the Bernoulli's equation. Here also, when we apply Bernoulli's equation between A and D, that is reservoir A and junction D. So reservoir A is subjected to atmosphere pressure and steady state conditions. So only thing remaining in the Bernoulli's equation is ZA. PA by rho G, VA square by 2G are all will be cancelled out. So left hand side we only have ZA. And in the case of junction D, this is not the atmospheric pressure. So we will have a pressure PD by rho G. And since it is a junction, there will not be any velocity will be 0, and the height is ZD plus the head loss due to friction HF1. We are calling it equation number 1. Now the flow from D to B, applying Bernoulli's equation between D and B. Again D, here the applying Bernoulli's equation we can write ZD plus PD by rho G. And for B, again it is a steady state condition atmosphere pressure, so the only thing is ZB plus the losses happening in this flow. Similarly, applying Bernoulli's equation from D to C also we can write. So this is equation 2, this is equation 3. So from continuity equation we can say that discharge through AD should be equal to discharge through DB and DC. So we can write discharge means Q is equal to AV. So we can write pi by 4 D1 square V1 is equal to pi by 4 D2 square V2 plus pi by 4 D3 square V3. Cancelling out the pi by 4 in common, and we will write the equation as like this. So if you clearly observe this equation, there are four unknowns, V1, V2 and V3, and PD by rho G, and there are four equations. So here so there are four unknowns and four equations, so which can be easily be solved. So now let us look at a numerical problem on branched pipes. Three reservoirs A, B and C are connected by a pipe as shown in this figure. So this figure will be given in the problem. Find the discharge into or from the reservoirs B and C. If the rate of flow from reservoirs A is 60 liters per second, find the height of water level in the reservoir C. Take coefficient of friction F is equal to 0.006 for all pipes. So you will be given a figure like this. So you are given the length L1, L2 and L3 of the three pipes respectively, and you are given D1, D2 and D3 for the three pipes, and the flow through the main pipe, that is AD, or rather the rate of discharge through the main pipe Q1 is given 0.06 meter cube per second, and this is our datum line. So this is the height of the first reservoir, that is a reservoir E. So we can say that this is ZA, and similarly this is ZB, 38 meters is ZB, and we have to find this ZC. So listing the given things once again, we can write L1 is equal to 1200 meter, D1 is 0.3 meter, Q1 discharge through the main pipe AD 0.06 meter cube per second, and ZA is given, L2 D2 is given, ZB is given, L3 D3 is given, ZC is not given. We have to find out ZC. As we have seen earlier, we will apply Bernoulli's equation between points E and D, between points E which is a reservoir, and D, or rather between A and D. So we can write ZA is equal to ZD plus PD by rho G plus HF1. As I have mentioned earlier, LHS will only have ZA because A means it is a reservoir. A reservoir is exposed to atmosphere, so it is atmosphere pressure. So PA by rho G will be 0. Similarly, it is steady condition, so VA square by 2G etc. will also be 0. So we are left with only these things in the Bernoulli's equation. Now in this, HF1 is equal to 4FL1 V1 square by 2G D1, wherein we can write this V1 square as V1 is equal to Q by A1, Q1 by area. Q1 is given, that is 0.06 meter cube per second, by area is given. So we'll get the value of HF1 as 3.518 meters. Now substituting this value here in this equation and rewriting this equation, we can write ZA is equal to ZD plus PD by rho G plus, in the place of HF1 we will write 3.158, or ZA value we already know, it is 40 meters. So we can write 40 is equal to this thing, or rewriting ZD plus P1 by rho G is which is equal to 40 minus 3.518, which is 36.482 meters. So this ZD plus P1 by rho G, this is known as piezometric head at D. The piezometric head means it is a sum of ZD plus P1 by rho G. So the piezometric at D is 36.482. So an important thing to note here is that the height here, this much height is 36.482, but ZB is at a height of 38 meters. So water will flow from higher energy level to lower energy level. So from the reservoir E to D, the flow is like this, and from once it reaches the junction, since the junction is at a height of 36.482 meters and ZB is at a height of 38.38 meters, so the water will flow from higher energy to the lower energy. So the flow is like this from B to D. Hence we can write that water flows from B to D. Now again, applying Bernoulli's equation between B and D, write this as ZB is equal to ZD plus PD by rho G plus HF2. So we have already got the value of ZD plus PD by rho G. So substituting that value, HF2 is equal to ZB value we already know 38. So 38 minus 36.482, which is 1.518 meters, which is HF2. Now We already know the equation of HF2, that is Darcy's Weisbach equation, 4f L2 V2 square by 2g d2. So substituting the value of HF2, we will substitute this value, and we do not know the value of V2. So from that we will get the value of V2 as 0.643 meter per second. Once we get the value of V2, we can easily find out the discharge Q2. Q2 is equal to AV2, which is equal to 0.02 meter cube per second, or 20.2 liters per second. So we have got the answer for the first part, that is the discharge from reservoir B. Now we have to find out the discharge from or into the reservoir C, and also this ZC. So let us look at that. So now in similar ways we apply Bernoulli's equation between point D and C, between this junction D and to the reservoir G reservoir, or from D to C. So ZT plus PD by rho G is equal to ZC is again reservoir plus HF3. So this value we already know is equal to ZC plus 4FL L3 V3 square by 2G D3. So here again V3 square means we can write V3 is equal to Q3 by pi by 4 D3 square. We do not know the value of Q3, but we know from the continuity equation we can write like this: Q1 plus Q2 should be equal to Q3. That is, this plus this inflow should be equal to outflow. Therefore, if this is Q1, this is Q2, and this is Q3. So Q1 plus Q2 should be equal to Q3. So Q3 will be Q1 plus Q2, which is equal to 0.0802 meter cube per second. Substituting the value, we will get the value of V3, 1.134 meter per second. And again substituting this V3 value here, we will get the value of ZC, that is 32.288 meter. So in this case, in this way, we solve the problems related to branch pipe. So hope you have understood this section, which involved parallel pipes and also flow through branched pipes.